How about another way? Okay, I'm going to show you another approach which in some sense is easier to understand, but it's actually not as good. That's why I showed you the other one first. All right. So here I'm using the same equation again, now using uv1 as being projectively similar to m times xyz1. But remember, if m can be changed by a scale value without affecting anything, then I could divide all the values by whatever that was on the bottom right-hand corner of m. What I would get out would be a 1 here. So I can just put a 1 in the bottom right-hand corner of that matrix. And the reason I do that is now my equations for ui and vi become this. All right? And what you'll notice is I now have terms when I multiply out, the ones in the denominator multiply ui and vi, which remember, those are knowns because those are the locations of the points in the image. So I now have terms that don't have the variables in them. That's why this is referred to as the inhomogeneous solution. And one of the reasons this is not as good is suppose the original M23 was supposed to be much, much smaller than the other values, that is, close to 0 compared to the others. Well, you've just set a number that was supposed to be really close to 0 to 1. That's dangerous with respect to numerical stability. So in general, and also in terms of overall minimization, doing the singular value decomposition or doing the eigenvector finding on A transpose A is the preferred method. And by the way, it's one line in MATLAB, so you might as well just do it. So what I just told you is referred to as the direct linear calibration or transformation method. It has a couple of advantages. One is it's pretty simple and to formulate and to solve. Like I said, it's literally, you just take your points, you make that A matrix, you then do some SVD, you pull out the column, bang, there's your M. Now these methods are referred to as minimizing an algebraic error, because essentially what we did was we set AM, we fixed M to be a unit vector, and then algebraically found the M that gave us the smallest algebraic magnitude of AM. There are some disadvantages to this method. First is that it doesn't directly tell you about the camera parameters, but we'll fix some of that in just a minute. It's also approximate because that M was based upon a particular matrix based upon pure extrinsic and intrinsic projection. What if we had something like radial distortion that we could actually model, but we couldn't model within our projective transform equation? How would we do that? Suppose I actually knew the focal length, right? I went out and bought a really expensive lens with focal length 3.746586, really precise millimeters. I don't want my M screwing with that. It needs to stay that value. I want to come up with the minimum solution using that precise value. And then finally, another problem, I put down mostly, I think it's just another one of those problems. It's not actually minimizing the thing that I really want minimized. It's minimizing this kind of cute algebraic trick that I had. So what is it that I actually want to minimize? Clearly, the amount of weight I put on every holiday. But besides that, what? Okay, that was not even a funny joke, but it was going too long without any jokes. So what is the right error function? Well, we refer to this error function as the geometric error, and it works as follows. Let's suppose I have some points in the world, capital Xi, and here they are shown in yellow. And furthermore, let's suppose I have an image, and I know where those points are in the image, and those are the red Xi's here, and these are these little red points here. Now, when I specify a camera projection, some sort of an M, right, what I'm saying is I know where those capital Xi's, the real points, are supposed to project to the image plane. And what I want to do is I want to find the M that gives me the smallest distance between the predicted Xi's and the ones that I actually found. And that's what this equation here says. What it says is we have an error function that is a sum of the distances between the observed points, those are the red Xi's, and the predicted image locations, the white Xi's here, of where the particular M predicts that the points in the world would land in the image. And what I want to do is I want to find the M that minimizes that value. And now what's kind of cool is I might have a more complicated mapping from points in the world to my 2D points that include things like modeling radial distortion, but fix for me the focal length. The idea is I'd have some great big nonlinear function that does the full projection, and what I want to do is I want to minimize this error function by manipulating the parameters of that big nonlinear function. And you might do that using your favorite Levenberg-Marquardt or some other way of doing nonlinear minimization. So if you read about this in a book and it says the gold standard, well, the gold standard of this type of work is the book on multi-view geometry by Hartley and Zisserman. What they refer to as the gold standard of calibration is, given some number of points greater than or equal to, but should be greater than 6, where you have 3D to 2D point correspondences, the way to find, they refer to as the maximum likelihood estimate. We could talk about why that's the case later. I'll tell you right now. You're assuming that the place that you located the points in the image was perturbed by a little bit of Gaussian noise, so you maximize the likelihood by making that distance as small as possible, and you want to minimize the square error if it's a Gaussian error. So the way you do that is as follows. You first compute a linear solution. Now, Hartley and Zisserman talk a little bit, and this is for those of you who are going to be more involved in doing some of this. What you might want to do is, if you're measuring your points out here in meters, you might have some big numbers or small numbers depending upon your coordinate system. Your size of your image, you may have different pixel values. They do a normalization so that everything sort of goes between 0 and 1 to try to get numerical stability. So when they do that, they create new external world points and new image points. You can do that or not. Then what you do is you solve the thing I showed you before, the direct linear transformation using typically the eigenvector approach. That gives you a starting point for the M matrix, which gives you a starting point for your nonlinear function. And then what you can do is you can try, using the M, you project the points, and then you can minimize that total distance, that's what's written down below, using, like I said, your favorite nonlinear method. After you've done all that, if you've done the normalization, you have to denormalize or translate back from the normalized methods. So that's how you get out your M. And that's what they refer to as the gold standard algorithm of calibration. We only use bronze, which is why in your problem set, you're going to use just the direct linear method. And you're going to see that even without, I will tell you this, that the first time we did this, we had people do the normalization, and it turns out the normalization buys you some, but not a lot. When we do it this time, you can use the normalization or not. So now we have M. Now we know that M encodes all the parameters, the extrinsic parameters and the intrinsics. So we should be able to find things about the camera from M. For example, the focal length, which would be an intrinsic. Or how about the camera center? In order to be able to do the projection, the camera center, remember the translation vector that translates from the world coordinate to the camera center? That, if we just knew that translational value, that would tell us the location of the camera center in the world coordinate frame. So we should be able to get that directly from the M matrix. So I'm going to tell you about two ways of doing that. Sort of the pure way, which is beautiful, and then the easy way. So we'll start with the pure way. Here's a slight change in notation just to pull out our parts. Okay, so we have our matrix M, and I'm just going to assume that M, which is a 3 by 4, is going to be made up of this 3 by 3, which I'll call Q, and B is just this 3 by 1. It's just a vector. Okay, so we've got Q and B. I'm going to claim that the center, C, which is a point, which I'm going to represent as a vector, is in the null space of the projection matrix. And what that means is that if you multiply M times C, it equals 0. And if you found such a C, that would be the camera center. And you should just trust me. Okay, maybe you don't trust me. Let me show you why that's true. All right? It's really pretty simple, except drawing it is painful. All right? Let's suppose I have some camera center C, and I've got some plane, and I have some point P that's out here. So I have a ray that goes from P to C, and I'm going to have a point X that's somewhere on that ray. Okay, so that's where X is. All right? So that's all that this equation says, that X is equal to something that's a blend between P and C. right? Lambda times p, 1 minus lambda times c. So given some m, that's the camera, the projection, all right, of x is just mx, and just by linear algebra, that projection is just lambda mp plus 1 minus lambda mc. Now for any point p, all the points on that ray have to land at the image of p. So any point p, all the points on this ray have to land at the same point on the image. Okay? So any point x along here will land at that same point, no matter what lambda is. Well, if this equation has to be true no matter what lambda is, and it has to land at mp, because lambda might be 1, that means that this value, mc, has to be equal to 0. So if c is the center, mc equals 0. And that's why I said before that the center C can just be found by finding the null space of the projection matrix M. That wasn't too painful. But suppose you actually wanted to do something useful. What would be the easy way of doing that? Well, the easy way is I just give you the formula. So if M is equal to QB, as I said before, then the center is just found by taking this quantity above that quantity in a vector. So this is remember Q is a 3 by 3, so minus Q inverse is a 3 by 3, B is a 3 by 1, so this is a 3 by 1, and then I add the 1 there. That is the vector that is the camera center in the world coordinate frame. So if I made, the corner of that table that you can't see, there's really a corner over there, if I said that's the origin, all right, and this way is X, and this way is Y, and that way is Z. And then I have a camera here, and I took a look at a bunch of points here, and I gave you the value of those points in this coordinate system. And then I located those points in my image plane. And then I did all that math to compute that M vector, and that M matrix. And then I pulled out the 3 by 3 and called that Q, and 3 by 1 and called that B. And then I took minus Q inverse times B over 1. That vector would be the actual location of this camera in that world coordinate system. Pretty cool. Finally, and this is the half bit that I was telling you about, there's an alternative way of doing calibration, which is pretty cool. And in fact, it's really what everybody is using today, because typically you don't have all these points. And it's a way of getting the intrinsics, and then if you know where you put these checkerboards, it's extrinsics. Basically, what you do is you take a checkerboard and you move it around, and you can end up calibrating the camera with respect to that checkerboard. The reason everybody uses that these days is that there's, first of all, you can print out a checkerboard, and the checkerboard has to be on a plane. Well, that's easy. You print out a checkerboard. You got to make sure your printer doesn't screw things up. You got to make sure that it actually comes out that squares are squares. You mount it on something that's a nice piece of rigid cardboard or foam core, and you don't have to know the positions and orientations in order to get the intrinsics of the camera, and then later you can get the intrinsics as well. And why does everybody use this? Because the code is easily available online. OpenCV supports this directly. We list here a MATLAB version of it. If you go to Zhengyu Zhang's website, he's like Dr. Calibration. He did spectacular work for us, these etc. in calibration. I'll also tell you that there's something cool you can do, and in fact a student of mine, Kelsey Hawkins, did this, and I think the code is made publicly available. If you take a checkerboard and you mount it on the end of a robot arm, and remember, a robot knows where its arm is in terms of its coordinate system. If you also know, let's say, the offset of that checkerboard from the end effector, the hand, then what you can do is with a camera, you can just move that checkerboard around using the robot. And of course, we know the 3D location of the checkerboard at every point in time that we take an image. And so by taking those images of the checkerboard, you end up calibrating the camera to the robot's coordinate system. So it's a cool use of doing this directly within robotics. So this concludes the lesson on calibration. In the homework, you're going to use the theory we developed for the direct linear calibration, and we'll give you those images that have the three-dimensional locations of the points, and you get the images, and you have to solve for the calibration. And it's interesting that you can actually recover that relatively precisely. In the next lessons, what we're going to do is we're going to move away from the notion of rigidly calibrating the camera to the world